Hi, I'd like to talk about the problem jewelry box that we did recently. So this was an optimization problem. In this problem, you were given a rectangle, and this rectangle had a length x, and it had a height y, and you were being asked to cut out four square-sized or square-shaped corners of area h times h. And after those have been cut out, then you would fold the remaining paper and you would fold those flaps up, and this would create a box, and you were asked to maximize the volume of this box. So this volume, of course, depends on h, the size of those squares of those that you cut out, and it is h times x minus 2h times y minus 2h. And you're basically asked to find an local maximum of this function. And so this is just basic calculus, right? You would look at the derivative and you would set that to 0. And the derivative of this is a quadratic function, and you can easily solve for this. Now, the function that is involved here is one that, if you were to plot it, right, it has a root at 0, h is equal to 0, and it also has a root at, let's say, x over 2, okay? Because here v of x over 2 is also 0, another one at y over 2. And so the function, being a cubic function, is probably going to look something like this. And we are interested in this point here, in finding this point. Okay, so far I said this is all kind of high school calculus, and it can be solved this way, and we probably should solve it this way, right? I'm going to show the code here. I'm not going to spend time typing this in. So in this case, we would solve this with pencil and paper, and we would find that a quadratic equation a times h squared plus b times h plus c times 0 needs to be solved, and then we want to find the maximum of the volume of h, for h in those solutions. Okay, and that works just fine for this problem. We would find this volume function for the solutions of this quadratic equations, and here I'm using the middle school formula for the quadratic equation, the naive formula, which is good enough here in this case. I call it naive formula because there's one that is better, that is more numerically stable, but it's not necessary to use it here. Okay, so now let us pretend though that um, the maybe we didn't know how to do this, or let's pretend that the function actually doesn't lend itself to an explicit solution, right? What if v of h had been a polynomial of degree 5 or 6, right? Where we would not be able to derive an explicit solution to find the root of the derivative. So more generally, what I'm interested in is to be able to find a minimum of a convex function. Okay, so let's say we have a function. This function is like this. It's called convex because any 2 points on this function, if I connected them, then no, this one here. If I connected them, then the line connecting them would be above this function, right? A function that's shaped like this is called concave. And so this is a convex function. What I'm interested in is finding or devising an algorithm that can be used to find a local minimum of such a function within an interval. This interval here would be maybe L and R, left and right. And the idea behind finding those minima is as follows. Okay, we will be splitting the interval into 3 different parts. Okay, so we're going to split them into thirds, and because we split into 3 parts, that's why this search will be called a ternary search. Okay, so it splits into 3 parts, and then the idea is to evaluate this function at those 2 midpoints. Okay, and here in this case, for example, if you can see that the value of that function, so let's call this one m1 and this one m2, And so in this case here, if we see that the function at m1 is less than the value of the function at m2, then we know for a fact that this extremum cannot be in this area here. Okay, so we can rule this one out, and we would then have a revised smaller interval to consider between L and M2. And we're going to repeat this process until we have shrunk the interval to be small enough that we can then announce the solution, the value at which this function reaches its local minimum. Okay. So this is the idea. Let's see if we can code this idea. Okay, so to that end, I've prepared a starter code here, and with a fast scanner, and we're reading in those values x and y. So the function that we want to optimize, I'm going to write this using Java function syntax. I'm going to call it f. This function takes the value h, and what does it return? Well, it returns h times x minus 2 times h times y minus 2 times h. So this is the function that we want to optimize. Now, we generally think of convex function, so we want to find the minimum. Here, the problem asks us to find the maximum, so we will negate this function. Okay? So we need to be able to find a value h that minimizes this function f within the interval of 0 and the smaller of x divided by 2 and y divided by 2. This is the interval of interest where this local optimum lies. And then this is what we need to, so our output then is in the volume where we apply this function at h. And since we negated the function, we need to do the negative of that. And this is here what the problem wants us to output. Okay. So now what's left to do is to write this function called minimize. Okay. So this minimize function, it takes a double function f. It takes a left bound L, and it takes a right bound R. Okay. So now this is where we will be making the interval smaller and smaller. We're going to repeat this until we're done. So we'll write this as an infinite loop where we need to check if it's time to break. Okay, and if that's time, we're going to talk about how to do this in a second. But if there's time to break, then we would return, and so we're now between L and R, and typically one returns the middle of the two. Okay, so if it's not time to return, now we need to find those 2 points, M1 and M2. Okay, so let me show this here. So this is the function, this is L, this is R, and we need to find these points M1 and M2 that represent these thirds. Okay, so this would be, in this case, it would be the weighted average of left plus right, and the way I usually write this is by factoring out the 1/3. Okay, like this. And then the one on the right would be similarly the weighted average in this direction. Now the two need to be compared. We need to say f, and apply this function to m1. We're going to apply this function to m2. Okay? And we need to compare those two, and then take an action depending on which one it is. Okay. So suppose the function goes like this. Okay. So then the value here and this value there, so f1 would be less than f of m2, and in this case I need to cut out the third interval. So what that means is that the right boundary moves to m2. Otherwise, the left boundary moves to m1. Okay? And so here the interval will be smaller and smaller with each iteration. Now, when should I stop? So the breaking condition will be something like r minus L. So r minus L needs to be small enough for us to have an accurate enough answer. Now, um, some competitors just make up a number here, and we think about it and come up with something um, that works a lot of the time, but in general it is risky and it can fail. And the reason for this is because whatever number you pick here, so if I pick a number 10 to the minus 8, okay, there may be two values R and L, so that function is searching for a minimum within a certain range, where we may not even find two floating point numbers that are less than 1.10 to the negative 8 apart. Because if you remember then on the number line, right, so we have 0 here, that the floating point numbers are densest in this area, and their density becomes less and less as they become larger, right? So this floating point gap here grows larger and larger. And so if you picked an absolute value, then it may be okay in here, but there may be some range where you can't reach this value. And so to avoid this, what we do is generally we do something else. So one method we can do is to say, well, first of all, we take the absolute value of the two, okay? And we're going to take the larger of the two. Okay. So if I have a math statically imported, I do. So let me write this. Let me write this like so. I'm going to take the larger of the absolute values here, and we're going to take the units in the last place. That's the size of the floating point gap here. And so this is very tight. But so let's maybe increase this by a factor of 10. Okay, so Um, and there's also a special accommodation we have to make for when the actually no, we should with this one. Yeah, so if L and R are really small, there's probably no point in ever to go smaller than 10 to the negative 16. So let's make this our sort of our bound. Okay. Right, so let's see. Let's try this and see if this works. It does appear to work, so let's submit this for this problem. And it passed. Okay, so this is how we have implemented a ternary search function, and this ternary search function finds the minimum of this convex function. Now I want to I want to emphasize this idea that you should not pick an an arbitrary value to cut off. Let me explain what the problem is for a little bit here. Okay, so generally these functions, they can take different shapes. The function can be, it can be like this, or the function can be really super steep, like this. Okay, and the our breaking condition here is given in the x direction. Okay, this is basically how small can this interval be, or here how small can this interval be. Now, very often the problem will ask us to compute the y to some accuracy. So here in this case, the maximum volume was to be computed with an absolute or relative error of 10 to the negative 6. Okay, so the problem very often will give us a tolerance, either absolute or relative error in the y direction. And because we do not know how steep the slope of that function is at the point where we're searching, we cannot easily relate the required accuracy in terms of the y direction and translate it into an accuracy at the x direction. For that reason, we are devising an algorithm that allows us to search what we say to machine precision. That is, we will be making the x direction um, smaller and smaller, as small as possible, okay? So that we are approaching the floating point gap no matter where we are on the number line, and we do not depend on any given error bounds in the y direction, because we do not know the slope of this function, and we don't know how to translate how to translate this. Last comment: how efficient is that? Well, on average, each of the iterations of this loop here adds, I think it's either 1 bit or maybe 2/3 of a bit or so. But overall, this is typically less than about 100 iterations. In fact, some hackers here sometimes put a loop here where they go from I is equal to 0 to 100. With a lot of problem that just works without doing this. What I've done here, but this is a stopping condition that stops when machine precision has been reached, when we cannot further divide this interval on the x-axis, and then we have to stop, and we are not relating it to any required tolerances that the problem may specify for the value in the y direction.